No, unfortunately for you. Is the mic okay? Yeah. All right, so good afternoon. So a quick recap on what we saw yesterday. Basically, we saw a little compiler from imp to a virtual machine. And then we scratched our heads trying to find what kind of correctness property we should state and prove, and came to the conclusion that this so-called safe forward simulation was a good bet, especially because the target language, this virtual machine, has deterministic semantics. And then we realized that we actually proved half of that result, which is that if the source program terminates, then the compiled code also terminates and on the same state. And now, well, we have to see what happens if the source code does not terminate. Okay, and we need to have some formal characterization of what it means for an imp command not to terminate. And so this is what we are going to do. So let me start with a reminder. So this is the semantics that we've used for imp so far, taken from Benjamin Pierce's Software Foundation. So it's so-called the big step semantics or natural semantics. This command started in this state, terminates in that state. And so here are the rules as a quick recap. So skip does nothing, assignment modifies the store. For a sequence where you evaluate the first part, then the second part, taking this intermediate state as a starting state for C2. For an if, you select the appropriate branch and evaluate it. For a while, if the condition is false, you stop. And if it is true, you do the body and you redo the while. Okay, so pretty standard. And so that style of semantics has several good things about it. So it follows naturally the structure of programs. And Gilles Kahn, who promoted that style very strongly, called it natural semantics. It looks a lot like an interpreter, what an interpreter would do, same kind of recursive traversal of the term. It gives you powerful induction principles on the structure of evaluation derivations. So that's a powerful tool to reason about programs. And it's easy to extend with various structured constructs like functions, procedures, other form of loops, etc. Now it also has some weaknesses. For instance, unstructured constructs like goto are extremely hard to add. Concurrency is essentially impossible to do in that style. And it fails to characterize diverging executions. So basically, it characterizes terminating executions, and then it makes no difference between divergence or going wrong. Indeed, so for imp, it's not so bad because imp programs cannot go wrong. So you could say that an imp program diverges if and only if there is no final state such that C started in S terminates in S prime. Okay. In general, that's not true. If you take the simply typed lambda calculus, for instance, this property is simply equivalent to C diverges or goes wrong. And that's not very informative. Okay. And besides, these are negative characterizations, so hard to work with. What we really want is a positive characterization of divergence. Okay. And so this standard answer to that, and then I'll show a non-standard answer, but the standard answer is small step semantics or reduction semantics. So, you know, just like in the lambda calculus, you view computations as sequences of reductions. So you start with M, you contract a beta redex, and that gives you a residual term, M1, which represents what remains to be computed, and then you chain up reductions and see what happens. And so I don't know if Benjamin Pierce showed that, but in his SF notes, there's also a small step semantics for imp. So it's a reduction relation, but since we have an imperative language, it reduces pairs of a command and a state to a residual command and a modified state. And for instance, an assignment reduces to skip. There's nothing to be done afterwards in an updated state. For a sequence, you have two rules. If the left part of the sequence can reduce from C1 to C1 prime, then C1 C2 reduces to C1 prime C2. And if you're lucky, eventually you will reduce to skip semicolon some command, in which case, well, you remove the skip and then you focus on the remaining command. So likewise, an if then else. So if the condition is true, it reduces to its then branch, otherwise to its else branch. And this is a cool one. For a while loop, you just unroll it. Okay, so you rewrite it to if the condition, then C followed by yet another iteration of the loop, else skip. Okay, so that's the small step semantics for our language. And as usual, as we did with the machine, we can chain reductions and see what happens. So if we reach skip and some state S prime in a finite number of steps, then we say this is normal termination, and S prime is the final state. If we have an infinite sequence of reductions, then we diverge. Okay, and this here is our positive characterization of divergence. And then we could also go wrong. So after a finite sequence of reductions, we get to a C prime, S prime, that does not reduce, and where C prime, sorry, is not skip. So we are stuck, but we are not in a final state. So I think for imp, this cannot happen. Maybe that's even an exercise for you to prove that it cannot happen. But as soon as you enrich your language with several data types, for instance, then going wrong becomes possible. And the good news is that, so we now have two notions of termination, two semantics for terminating programs. Either I reduce to skip, or the big step semantics says I terminate an S prime, and that's the same S prime here and there. And the good thing is that they are equivalent. And I think there's a proof somewhere in my file called semantics.v. Let me see if I can find that for you. So what do we have here? Yeah, so this is a recap of the big step semantics. This is the small step semantics, just as we saw on the whiteboard, on the slides, but written in as a coq inductive predicate. And so we can even show that the step relation is deterministic. Probably need that at some point. Now we can form sequences. So termination, divergence, going wrong. This is the exercise I mentioned. It's not possible to go wrong for imp. So this is a little lemma that says that sequences of reductions, if you have a sequence of reductions from C to C prime, then you can put it in a sequence. So C followed by C2 will reduce all the way to C prime followed by C2. And so this is the first half of the equivalence I mentioned. And the proof is basically by induction on this derivation, okay, big step derivation, and then we form the reduction sequence. And it's a really simple proof. You can replay it if you want. But basically, there's one case per execution rule. So one for skip, where the reduction sequence is empty. Assignment, where we do exactly one reduction. Sequence, where we chain the reductions obtained. So you don't see the induction hypothesis, but here they are. So by induction hypothesis, we get those two very useful reduction sequences, and all we have to do is combine them together. And so on. So that's an easy result. And the reverse implication is tricky. If you try to prove it directly, you're going to suffer. Trying to split reduction sequences into halves and so on. Actually, the key lemma is this. So say you have one step of reduction. Okay, so one small step, and then you finish evaluation using the big step semantics. All right. So from that state on, you're no longer doing reductions. You're just jumping to the final result with the big step semantics. Then you can absorb this reduction step into the big step evaluation and build a big step evaluation that will go from C1 to the final state immediately. And so it's kind of a technical lemma. There's plenty of inversions and case analysis to be done. But and then now you can do a lovely induction on this reduction sequence, okay? Because if it is empty, then you'll just have to prove that skip evaluates to skip in ST reduces to evaluates to ST, which is obvious. And then afterwards, you get an induction hypothesis and one step of reduction, and you conclude with a lemma. So that's a neat little proof. And just to reassure you that basically we have several semantics, but they all describe the same behaviors. Okay, so pros and cons for small step semantics. Well, it's unquestionable. I mean, it gives a clean characterization of the three behaviors of interest: termination, divergence, going wrong. Everyone agrees about that. It extends even to unstructured constructs, so you can do goto, you can do concurrency. I mean, the whole field of process calculi is based on transition relations, right? And it is de facto standard in the type systems community and in the concurrency community. There are a few cons, though. For instance, well, it does not really follow the structure of programs. In particular, you don't have an induction principle. Okay, you can do an induction on the number of reduction steps, but that's not a very powerful induction principle. It's less powerful than what you get with inducting over a big step derivation. So this one is one of my pet peeves. This is not the way interpreters have written. Okay, if you implement a programming language, it's not going to rewrite your program, your source program, step after step after step after step. If you do that, your interpreter is going to be big and slow. And then maybe we will see some of that later. When your language is rich enough, you need to extend a little bit the syntax of terms with terms that are not present in source programs but appear during reduction. For instance, if you add procedures to IMP, you will need some extra syntactic forms to remember call context, okay, that I am evaluating this statement, but because it is part of that call, which itself is part of that statement, and so on. And so basically there's a surface syntax in which you write programs, and then there's some extensions in which you do reductions. And some people are fine with that, some people find this slightly ugly. Your choice. Yes, please.
So, I mean, it's possible to have big steps semantics goes wrong. You just have to tell it explicitly when things go wrong and have an option type for the
yes, indeed. So for going wrong behaviors, you can write big step rules. So as you said, either you extend that relation to say OK of S prime or crash. Or you can also give a separate set of rules that say C of S, C in S crashes. But then you still have no positive characterization of C in S diverges. Okay, C in S diverges will still be the negation of either I terminate or I go wrong. But yes, it can be done. Are there famous examples of that? Can't remember if the definition of standard ML, for instance, which is in big step, includes rules for going wrong. Perhaps not. But let me propose you another way to think about big step. This one is fun. Is to use co-induction. And let's step back a little. One way to view big step semantics for termination is as adding some structure to terminating sequences of reductions. And let me show you an example. Say you have a sequence CC prime and it terminates. So eventually it reduces to skip. Okay. Now if you look long and hard at this reduction sequence, you will see that necessarily it starts by reducing in C, okay, to C1, to C2, until that left part is skip. Okay, that's the only thing you can do with the rules I showed you. At which point the skip disappears and then we start reducing C prime. And so in this sequence, there is a terminating reduction sequence for C. C in S goes to C1 in S1, goes to skip in S2. And then there's a terminating sequence for C prime. C prime in C2 goes to skip in S3. And that's exactly what the big step rule tells you. Okay, from C1, C1 takes you from S to S1, or maybe there should be S2 actually, and C2 takes you from S2 to S3, and therefore the sequence takes you from S to S3. Well, why don't we play the same game for an infinite sequence of reductions?